Hey everyone, welcome back to my channel EduVibe. In today's lesson, we are starting with another topic of the atomic physics, which is detecting and measuring the subatomic particles. Now we are start with some theory part. We involved some equations in that too, but the old one in the previous 3 units. Now we are introducing the subatomic particles and in this lesson we are basically focusing on that how can we detect or measuring those subatomic particles. So uh, for doing this, we have two types of chambers. We have a cloud chambers and we have a bubble chambers. So what is a cloud chambers? Cloud chambers are looking like that. This is like a blueprint of that thing. If you're doing the experimental thing with that, you get this type of thing as a cloud chamber. So in 1894, the Scottish physicist Charles Wilson was fascinated by the odd shadows that can sometimes be formed on cloud tops by mountain climbs. To further investigate the cloud formation in the moisture, Wilson developed a cloud chamber in which he kept the air inside supersaturated with water. So he was fascinated about the shadows, which are the odd shadows that sometimes found on the cloud tops as by the mountain climbers. So the further investigate when he do with the formation in the marsh air, the Wilson developed the cloud chamber thing, is the theory of that, and where he kept the air inside the supersaturated water. Air can hold a certain amount of vapor. You know, when there's like a lake or a water thing, the evaporate thing. So they mentioned air can hold that very certain amount of that vapors. Supersaturated means the air is holding the more vapor than it normally would under the particular conditions. In some particular conditions, the supersaturated means that when the air is holding the more vapor than usual, and normally under the some particular conditions. It is in the very delicate state that can easily be disturbed to cause congestion of the vapor into liquid droplets. So it is very delicate state, and you know that after the vapors they do the condensation thing, where they form from like gaseous to the liquid droplets, which causes the rain. And it is similar to the tracks you see the sky when an aircraft passes over. So that's the whole theory of cloud chamber. When they are like from this, they can detecting subatomic particles. There are subatomic particles in the air, so they can detect those particles, and by looking that by doing that blueprint thing. And there's application about that this is similar tracks you can see on the sky when an aircraft passes over. You can see there's uh, uh, some fog-like structure like the white thing. You can see a vapor trail. This is a vapor trail that aircraft then passes over that. By the combustion of the azotic gases, these vapor trails show the path that aircraft has taken. So these are the paths that these shows the paths of aircraft which they taken when they pass through that area. So that's all the cloud chamber is more connecting to the vapors and the congestion of process. So these are like all the clouds thing, and we involve the supersaturated air and how they normally and depend the vapors thing. So these are all the cloud chambers to get in the subatomic particles. We have another thing which is called the bubble chambers. So we can also do the Z opposite of the cloud chamber by having a chamber filled with the liquefying gas such as hydrogen, helium, propane, and the ozone. So we can do this cloud chamber Z opposite with that the bubble chamber. So we have a chamber filled with a liquefying gas. We have some chamber which has a liquefying gas, which is hydrogen, helium, propane, anything. That is such a low pressure that it is not on the edge of the boiling back into the gas. They have a low pressure, and as a charged particle passes through this liquid, causes the gas in the chamber to boil, leaving a trail of bubbles along its path. So what when we do that, we have a chamber like this, we have some chamber, and we have some gases. We have a hydrogen or we have a helium thing. We this way which has a low pressure in it. Make sure this have a low pressure, and when we put some charged particle passes through that liquid, you can see the gas in the chamber, the boil out. They will boil in that and leaving the bubbles along its path like this thing. And this is known as a bubble chamber. It was developed by the American physicist in 1952. Cloud and bubble chambers are usually operated with a constant magnetic field. So they also involve some magnetic field in it, which is constant. perpendicular to the path of the particles. This allows us to observe the spiral patterns in a chamber. You can see there are some spiral things. You can see there are some spiral things. There are spiral patterns, and over there too, we have some spiral things over there like this. So they both have some same patterns. If we measure the radius of their path, we're going to determine the things like the charge to mass ratio. If you want to doing some measurement of this radius, we can do some charge to mass ratio thing, which is given by the Thomson model. And you know that this is again the same thing we did in this chapter, and we again do this thing in that topic too, with the identification of the particles. If we do one drawback to using the cloud and bubble chamber, that they cannot detect the neutral particles. They only detect the charged particles, the electron, proton, and their antiparticles too, but do not do with the neutral thing, which is a neutron. They don't do anything with the neutral. They don't detect the neutron thing in that thing. Only ions are affected by the electric and the magnetic fields. Either they have a positive charge, either they have a or negative charge. They do only that affected by the electric and the magnetic fields. So these are the drawback of this. They cannot detect the neutral particles. So these are the two chambers, and we have to know about these chambers because these are important things. The theory is important in this. You sometimes add the question related to the theory. Sometimes add the question like this, which involve the charge to mass ratio again, and all the topics we did in the last 3 units. So for the particle traits down shown below, there's some same thing, and resume they were made by the particles moving at the speed of the 0.10 c, which is like kind of, you can say the c is a light or speed of the light because it's a small c, through a uniform magnetic field of 30 meter Tesla into the page. The initial radius of the each track is 5.7 mm. Determine the charge to mass ratio of the particles. So this is the velocity given to you. This is speed given to you. So you have 0.10 c, which is 0.10 into 10 raised to power 3.0 10 raised to power 8 meter per second. You can multiply this by the speed of mass, and you get 3.0 into 10 raised to power 7 meter per second. This is your actual speed elements. So the particle tracks. There's no picture over there, but this kind of like that pictures, and you can see there are the spirals on it, which means there's a circular motion involved in it. And also you can see from here that they also have the magnetic field over there, which is constant. So which means the circular motion magnetic field combination we can use in this. So we can use these things, and from here too you can find the charge to mass ratio. So you know this is mv square upon r is equal to qv times magnetic field. mv upon r is equal to q v, that v cancel out. You want q upon m, so you can isolate these both things and you get v upon magnetic field times r. So when you put the things in, so we have a speed of 3.0 10 raised to power 7 meter per second. You have magnetic field, which is 30 point, and meter has the value of 10 raised to minus 3 Tesla, and we have this given 5.7 mm, which is 5.7 into 10 raised to minus 3 meters. So when you calculate this whole thing, you get q upon m of about 1.754 into 10 raised to power 11 coulombs per kg, which is actually the 1.75 into 10 raised to power 11 coulomb per kg. So this is your charge to mass ratio of that particle. So the same thing you use, which you use in Thomson model in the first lesson. That same thing you use in this too. And we have a related question of the previous that question, which you can do that example too. So for the subatomic particle undergoing deflection under the influence of the constant magnetic field. Now the constant magnetic field we have. Determine the expression for the particle's momentum. Now we want a expression for the particle's momentum. Basically, we want a momentum. Use this expression to determine the momentum of the particle in the previous example. You may assume the particles in a previous question are the electron-positron pair. So we have electron-positron pair. They've given us that the pair of that, and we have to use the same formula in this. So if I start from here, so I give you some things. So we use this formula, Fc is equal to Fm, and we have mv square r upon r, which is qvb. From here, which you cut those things, and you get mv upon r, which is q magnetic field. You want a momentum thing. You want a momentum of this. So you can see that m times v is basically equal to the momentum. So you get the momentum upon r now, which is this thing. From here, when you r goes over there, they multiply with that thing and you get this thing. So from here you can find the momentum. So charge, you have 1.6 10 raised to power minus 19 coulombs, which for the electron. Magnetic field stays the same, you can use from the previous question. And the R stays the same, we used from the previous question. When you calculate this, you get about 2.7 into 10 raised to minus 23 kg dot meter per second. So this is your momentum. So these all both questions are connected to each other. You have to do something like over there when you cut the V's and you get this, and you get this formula for momentum from the same thing. So that's all for you can do with the chambers thing, the retinal measuring then, and you can involve the charge to mass ratio in this to like doing some measurements of the radius. So you get one theory question or you get some calculation like that. So you have to be prepared for that topic too. So this is all for this lesson. Let me say if you have to vibe, learn smart, not harder. Please like, share, and subscribe to my channel. If you have any questions, let me know in the comment section. See you in the next lesson. Till then, with EduVibe.